Very nice to be here, and I enjoyed a lot of things from yesterday. And sorry I couldn't be here on Monday. So the date is wrong. It will be fixed in the version online, hopefully. Oh, what happened? Yeah. It's not full screen. Okay. So I'm going to refer to lots of other papers when we go through the material, but I'll in particular mention what I've been doing over the last year and a half or so, which came out in these 4 papers, and we're thinking about a few more related ideas. This subject is intertwined between dynamics in the context of more condensed matter, but also there is some generalized symmetry that is important for that subject. But I'm not going to talk about the generalized symmetry aspect today. So I'll concentrate more on the dynamics, that is on the dynamics part, less on the symmetries part. And if there are any questions, please stop me. So the setup is some quantum critical point in this space-time dimensions. So the number of space dimensions is going to be d-1. Just it's convenient for my equations in various places. So we'll be at a quantum critical point at 0 temperature. That will be the setup for the whole talk. So when people talk about quantum critical points, I'll be mostly interested in the case where there's an emergent Lorentz invariance, and the critical point is in fact a fully fledged d-dimensional conformal field theory with conformal symmetry, just because that's the simplest case where I can prove many results, as you'll see. So the literature of that subject is of course vast. It goes back to the late 60s, probably from when people started to understand that critical phenomena come along with conformal symmetry, which is probably in the late 60s. And a lot is known about correlation functions of local operators. It was a huge subject where we learned about critical exponents, and nowadays there's a lot of development of 4-point functions, 3-point functions, this kind of stuff. So this is a very well-known subject. I won't talk about it today. I'm going to consider a subject that is a little bit more exotic, and very little is known about it, even though it's experimentally easily accessible and also very easily accessible in simulations. And this is the subject of point-like impurities in space. So if there is a point-like impurity in space at a critical point, in space-time it's a line defect. So when I say line defects, I mean in space-time. In space, there are going to be point-like impurities. Now, point-like impurities are of course not local operators. These are modifications of the Hamiltonian by a certain point-like perturbation. And so what is the subject of what can you ask about point-like impurities? You want to go to the infrared limit. So in the bulk, you're already at the critical point, so there is no renormalization in the bulk. But on the impurity, there could be a renormalization group flow, and you have to flow to the infrared of that impurity. So there is a localized renormalization group in this quantum mechanics on the impurity, so to speak. And the infrared of this impurity could be either completely trivial, in the sense that the impurity just disappears in the infrared. So if you go to the infrared limit of the impurity, Green's functions in the bulk would not see any deviations from the Green's functions in ordinary at an ordinary critical point without impurities. So that's when people say that the impurity is completely screened, that it just completely disappears in the infrared. Or the other scenario, which is possible, is that the impurity flows to a conformal impurity. And then Green's functions do detect the impurity, they decay algebraically from the impurity. So if you're like at the distance d here, you measure some local operators here, they would decay as the function of the distance from the impurity as some power, algebraically, so some dictated by the power of some power, inverse power of the distance. And then the impurity is conformal, There is no scale, neither in the bulk nor in the impurity. And that's the other scenario where the infrared is a conformal impurity. So the subject is basically to understand which impurities might exist in conformal filters and to understand which of them are conformal, which of them are transparent in the infrared. And you'll see there are lots of constructions which are very canonical and experimentally accessible. And there's some nice theory that you can develop. While a lot is known about the space of local operators, we have lots of rigorous results about correlation functions and the space of local operators and their scaling dimensions. Basically, nothing is known about conformal impurities except for very simple ray filters, perhaps.
So the question?
Yes.
So the correlation functions you're talking about, are they all away from the impurity, or is?
I'll talk about those.
Okay.
I'll tell you about the theory of this subject. Now, since you asked the question, it's a very good question. So there are bulk operators which act on the Hilbert space on the bulk. You think about it, it doesn't matter on the bulk spins. But there could be some degrees of freedom that are localized to the impurity. So there are also operators that act on the impurity. And these sets of operators are usually not the same. And their scaling dimensions are not the same. So there is a set of scaling dimensions for these set of operators. And there is a set of scaling dimensions and correlation functions for bulk operators. But they're connected by something, by an operator product expansion, like in Wilson's case. You can take a bulk operator and expand it in a singular power series in terms of defect operators. But you cannot do the opposite. You cannot re-express every defect operator in terms of bulk operators, but you can re-express bulk operators in terms of an infinite sum of defect operators. I'll show you how that works very soon. So the subject of line defects is actually historically played a huge role. As far as I know, Wilson came up with the whole idea of the renormalization group by studying a very special impurity that's called the Kondo impurity in 1+1 dimensions. So D equals 2. Also, this was the first instance of integrability in many-body quantum physics. In quantum field. Probably one of the first instances of integrability in some interesting energy flows in the continuum. I think the conformal symmetry came up in this context very early on. But this was all in 1+1. And if you ask what's known about these space-time dimensions, the answer is essentially nothing. So this is just a picture that what is a possible thing you could do. I'll talk a little bit more rigorously about it later on. On the lattice, let's say you have a spin half on some antiferromagnetic spin half spin code, the surface, and it's in a critical point. You can add an external spin S, which is not a spin a half, couple it to the bulk spins with some new coupling J naught, and ask what's the infrared limit. So this is very easy to simulate, and this is one example of an impurity. Okay, so this is so here I'm just listing, I'll talk about it in more detail, but lots of canonical constructions for impurities exist. If you do, this is a union of condensed matter and high energy physics. So in condensed matter, people talk about SPT defects. I'll talk about such an example later today. Later in this talk. Then there are charged impurities, which in high energy physics are called Wilson and 't Hooft loops. There are twist defects. There are anyons are basically examples of impurities. Something that's called in condensed matter repeating field defects, and I'll talk about it also. So there are lots of canonical constructions, and they appear in various applications. So first, I'll start from some general theorems. I want to show you some completely general results that can be proven, and then I'll apply them in a few examples. So that will be the outline of the talk. Any questions before I get into a little bit more details?
Are lines effect better than plane effect?
I can talk a little bit about plane. Actually, there are rigorous results that I just didn't want to talk about it too much. But there are also rigorous results about plane defects by now. Yeah, I think the point like impurities, perhaps we know the most. So, and also the rigorous results about point like impurities are stronger than for line defects. The rigorous results are stronger than for plane defects at the moment. But okay, so now in a little bit more detail, when we have a conformal impurity, it will preserve a subgroup of the full conformal symmetry. So you cannot preserve the full conformal symmetry with an impurity unless it's completely trivial impurity. So if it's not trivial, it's going to preserve an SL2R. That's the key. You can ignore it. This is the transverse rotations around the impurity. But SL2R is the key conformal subgroup that is preserved by the impurity. So what does SL2R consist of? It's like in conformal quantum mechanics. You have translations in time, you have rescaling, and you have a weird transformation, which cannot be easily understood intuitively, which corresponds to the third, which is a special conformal transformation that leaves the impurity intact. If the impurity is non-conformal, then all there is energy conservation. And in the infrared, these translations along the impurities enhanced to SL2R. You get scaling symmetry and a special conformal transformation. Okay, so these are the symmetries of the problem. And this is what I already responded to you. In this problem, there are bulk operators, but there are also defect operators. And the defect operators have their own scaling dimensions and SL2R cross SLD minus 1 quantum numbers. And in general, the space of defect operators has nothing to do with bulk operators. And their scaling dimensions have nothing to do with each other. So this is the bulk defect operator. Yes?
Can an impurity be scalar invariant but not conformal?
Probably it can be ruled out. There is some paper that I should have cited by Yu Nakayama that I think has some arguments to that effect that rules out that possibility under the assumption of unitarity and locality. It's a very similar argument to all the other arguments of that sort. So the very important conceptual thing is that there is an operator product expansion for bulk operators in terms of defect operators, but not the opposite. So you can expand any bulk operator, which is at X transverse away from the impurity, in terms of operators at the same time. So it's an expansion at fixed time with some powers that depend on the distance from the impurity, and the exponents depend on the scaling dimension of the defect operators and the bulk operators via this combination here. And as any operator product expansion, this is useful at short distances. A particularly important observable that condensed matter people simulate and measure, and we have experimental results, is the particular instance of the unit operator. So a unit operator can appear on the right-hand side of this expansion. So you can, when you expand the bulk operator, you can get the unit operator on the right-hand side. And there is a corresponding coefficient A, and that leads to a one-point function. So unlike a regular conformal field theories with no impurities where the one-point functions vanish, here the one-point function does not necessarily vanish, and it decays algebraically from the defect, as I said at the beginning. And the coefficient A is something that people measure. So there is lots of data on this coefficient in many examples.
This coefficient is universal.
This coefficient depends on the fixed point of the infrared impurity, and it's a universal characteristic of the conformal impurity. Yeah. So people measure it in many examples. Oh, sorry, this is the wrong slide. Okay. So now I'll tell you a little bit about rigorous results on this subject, and then we'll go through examples like explicit constructions. So one quantity that you can define, which makes no sense in ordinary Minkowski signature, so it's not easily measurable, it's the partition function of the impurity if you make it into a circle. So it's like the trace of the Hilbert space of the impurity, but it's a constructible circle in flat space in Euclidean signature. So it doesn't make sense in Minkowski signature. But if you study topological quantum field theory, this is what people do to measure the quantum dimension of an NER. So it's not a completely new idea to do such partition functions. So this partition function makes sense. You can do an argument. You can make an argument that if you apply this operator, R is the radius of this circle. So if you apply this operator to the partition function, you get something that's renormalization scheme invariant. So everybody's going to agree on it in the continuum limit, regardless of which scheme you use. It's generally a function of R, of the radius of the circle. But if the impurity is already tuned to a conformal fixed point is going to be R independent, and log G is like the analog of the quantum dimension of this conformal impurity. Okay, so log G is like you can associate a number if the impurity is already tuned to a conformal fixed point, which is the analog of the quantum dimension of the impurity. So this is what I'm saying here. You can think about at the fixed point of the impurity, the defect entropy. Sometimes we call it defect entropy. That's why little s is the notation we chose. So sometimes the defect entropy, so the defect entropy at the fixed point is sometimes also called log G, which is the quantum dimension.
This construction is to kill off the linear part in
Yes, you need to apply this differential operator to the partition function to get something that's scheme independent. Because when you have a word line of an external impurity of any sort, the ground state energy in that quantum mechanics is something that is dependent on the UV completion or on the lattice. And no, you cannot agree on it in the continuum.
Is it a perimeter contribution?
Yes, this kills the perimeter contribution. Yes.
Sorry, what is L?
L is the partition function of the line defect. Okay. So you take the partition function of the line defect, you apply a certain operator that is meant to make the partition function scheme independent, because partition functions are usually UV divergent. But if you apply this differential operator, it's going to be finite and scheme independent. You must do the same in topological quantum field theories, strictly speaking. It's just that when people introduce the subject, they're not careful about it. But it's done implicitly in that literature that people subtract off the perimeter contribution.
So L is not know anything but the bulk, right? It's purely.
Well, no, this is in the bulk.
Oh, okay.
You take a circle in the bulk CFT and you compute the partition function.
I see.
Yeah. Yeah, it's not okay. Of course, it's very hard to measure this quantum dimension. As you may remember, for anyons in topological field theories, this is always bigger than 1. G is always bigger than 1. There is a theorem that you can prove that in unitary topological field theories, the quantum dimension is positive. But we will see that for conformal defects, it's not true. There are many conformal defects with arbitrarily small g. It still has to be positive, I believe. I don't know if it was, yeah, it follows from unitarity, the g has to be positive. But we have many examples where g is arbitrarily small. So,
Do you have a philosophical understanding of why that happens? What it means?
yeah, I think there is some kind of intuition I can give you. So if you think about G as the number of degrees of freedom inside the enyon, so in topological field theories, there are no degrees of freedom in the bulk. There are just none. So there are some degrees of freedom on the enyon, like the degeneracy of the enyon. And it's intuitive that it's positive. But when you have degrees of freedom in the bulk, the presence of the impurity can push them out. So you could, the presence of the impurity could reduce the effective number of degrees of freedom near the impurity. And that would be associated with a negative defect entropy. A trivial impurity, of course, has G equals 1, like in topological field theory. Okay. Now you can think about our G flows on the defect by just ordinary deformations of the defect. It's like in statistical mechanics. If you have a conformal defect with an operator whose scaling dimension is smaller than 1, because it's a one-dimensional line, you can deform the line operator by an integral of this local operator, and you'll get an RG flow to a new conformal defect potentially. So this is just the setup of our G flows. You start from an ultraviolet conformal defect, you add the local operator, you get an infrared conformal defect. And this defect entropy, little s, that we just discussed, will be some function of the radius of the defect. And when the radius of the loop is huge, it's going to probe the quantum dimension of the infrared conformal fixed point. And when the radius is small, it's going to probe the ultraviolet quantum dimension of the conformal impurity. Okay? So the radius of the impurity is like the radius of this fictitious circle in Euclidean signature is like a gadget that tracks the RG flow. So some work that we published last year, we proved a weird identity about how this defect entropy changes as a function of the radius of the circle. So you can re-express it after some work as a 2-point function of energy density on the defect times a modulating factor, which is 1 minus cosine. It's a very long argument that I'm not going to repeat here, but happily, this is positive and this is positive. So that allows to prove a theorem that this defect entropy is negative definite. It has a negative definite gradient. And therefore, the quantum dimension must always decrease or not increase. Okay. So this is a general non-perturbative constraint on every impurity in a local quantum filter, that the quantum dimension must not increase in energy flow on the impurity. And this has very interesting applications for various defects in magnets, as I'll show you in a few minutes. Are there any questions about this? This is analogous to the Affleck-Ludwig theorem about quantum defects in 1+1, except that this is true in any number of dimensions in unitary local theories. So this is a vast generalization of Affleck-Ludwig, and it also provides a new subrule that is actually also true in 1+1. Now you might wonder what's the connection of this quantum dimension to entanglement entropy. In topological filters, there is a very beautiful connection. Maybe it was already understood by Levin when I'm not sure about the history. But so in topological filters, and also in 1+1 dimensions, there is a very beautiful connection between log G and the entanglement entropy of a region that contains the impurity at the center. And the connection is that they're the same. So the extra entanglement in the vacuum due to the impurity in 1+1 dimensions, as well as in topological field theories, is the same as log G. In 2016, Cassini, in 1+1 dimensions, the connection between the extra entanglement entropy and log G was pointed out by Cassini, Salazar-Landea, and Doroba. That's true in 1+1, and it pertains to the Affleck-Ludwig / Friedan-Konechny story. But later it was realized that this connection between log G and the added entanglement entropy is not true in higher dimensions. So the log G that I'm telling you about here is not connected to the extra entanglement entropy. It's not the same as the extra entanglement entropy in the vacuum with an impurity at the middle. But recently, just 2 or 3 months ago, there was another installment of the Cassini, Salazar, Landea, Doroba paper. So they published a new paper where they tried to make an argument for what is log G in higher dimensional impurities. I haven't completely understood the idea, but it involves entanglement on some light-like surfaces. So it's much more complicated to give a quantum information interpretation of this new log G that applies also for non-topological filters. So I don't have an intuitive understanding of what the idea is. Are there any questions about this?
So the intuition here is still that this impurity can push out degree of freedom, and so
Yes.
there is no chain.
There is just no beautiful connection to entanglement entropy in the region that contains the impurity. When you need to do something more complicated with entanglement entropy to get log G. That's what they did in this paper, but I haven't completely understood the idea yet. So I'll just now give you 4 different constructions of famous different constructions of impurities that appeared in the literature, and then we'll go over actual concrete examples. Each one will be of one of those types. So one example is to start from a trivial line defect into ultraviolet. So you have a completely trivial impurity in the ultraviolet. So if there is a transparent trivial impurity, the space of defect operators that you can deform by are essentially bulk operators that you can bring to the impurity, because there is no singularity when you bring a bulk operator to the defect. So you can just integrate bulk operators which have dimensions smaller than 1, and this triggers energy flow. So every field theory with an operator of a dimension smaller than 1 can be used to trigger some interesting energy flow on an impurity via this formula. And in condensed matter, this is called the pinning field defect, because you can think that bulk operators coupled to sources, like an external magnetic field, external magnetic, external magnetic field, external temperature, these kind of things. So they couple to external fields, local operators. So you can think about it as applying an external field at one point in space. So usually when we talk about a string system, we talk about applying a magnetic field everywhere in space, but you can also just apply a magnetic field on a few lattice sites. So that's this kind of, this would be called a thinning field defect or an external field defect. Now the G theorem that I told you about here, this theorem has a very interesting implication that immediately says that all such defects cannot be screened in the infrared. Because if G in the ultraviolet is 1, G in the infrared cannot be 1. It has to be strictly smaller than 1 by the inequality that they proved. And therefore, it cannot be a trivial unit defect. So this completely proves that thinning field defects must be non-trivial conformal filters in the long distance limit. And this was an open question in condensed matter for the thinning field defects in the XY model or the Isaac model. So this is settled, it has to be non-trivial, it cannot be screened. So an external field cannot be screened under those circumstances. A more complicated construction is that instead of just turning on an external field, you can add extra degrees of freedom and then couple them to the bulk. So this is like what condo type defect, that you have some quantum mechanical Lagrangian, take your favorite quantum mechanical model. It could be a particle moving on a sphere with 3 ground states, whatever. And you can couple it to any bulk CFT via subcouplings. So you could take a qubit and couple it to the bulk. There are many constructions. The SPT defects in condensed matter are of this type. I'll mention one example later. So that's a more general example of that, where you take a quantum mechanics with some non-trivial degrees of freedom rather than just one state.
What's TQM?
You have a quantum mechanics with some quantum mechanical operators, some operator in that quantum mechanics that you couple to the bulk.
Actually, so in the previous slide, actually, suppose I just consider a magnetic impurity
Yes.
at a critical point. So whether it can be screened or not is just another way of saying whether this the
The effective magnetic field.
whether it's relevant or irrelevant.
No, but even if it's relevant, the long distance limit could be trivial. The magnetic field would grow and then decrease. So the true magnetic field at long distances would have been 0. There are many examples of relevant perturbations that end up
being screened.
being screened.
Yeah, okay. Yeah, that's fine.
So this theorem, this G theorem, implies that it cannot be screened at long distances. Another construction is gauging. So you could have a quantum mechanical model with a symmetry G, and G could also be a symmetry of the bulk. So you could couple the gauge field to the current of the quantum mechanical model. So that would be like gauging the symmetry of the defect. And that's how we construct charged impurities. So when people talk about charge impurities in graphene or Wilson lines, that's the construction. We just gauge a symmetry of a quantum mechanical model. And finally, that's an example I won't talk about today because it's a very long story. There's something that's called the monodromy defect. It's a point-like defect around which bulk operators pick up a phase. So this is a completely canonical construction that exists in every system with a U1 symmetry.
So I'm just being very basic. So it's TQM. I mean, so you're defining that on the impurity, or
Yeah, you take a quantum mechanical model that's completely decoupled from the bulk, and then you couple them by some operators. And this is not of the same type because here you gauge. So it's not strictly speaking the same as coupling the operators, but if you're naive, it's almost the same because you can think about the gauge field as an operator. So the monodromy defect is a completely canonical object that exists in every system with a global symmetry. You can implement a global symmetry transformation around the defect. And then you can study the phase diagram of this impurity as a function of this parameter H. But I won't talk about it today, it's too convoluted. And also these various descriptions are interchanged by dualities. So many people here worked on, let's say, the recent boson fermion dualities. And essentially nothing is known about the space of conformal defects and how they're interchanged. by a boson fermion duality. But we have examples in supersymmetric theories where we know how various dualities interchange this description with this description and so on. So these descriptions are just constructions, but they may depend on the duality frame. Okay, any questions? Now I'll discuss the magnetic defect in the Wilson-Fisher fixed point, and we'll compare a little bit with simulations. So what is the construction? It's a Wilson-Fisher fixed point in space-time dimensions between 2 and 4, and you put a localized external magnetic field. I don't have a picture.
Strictly less than 2 and strictly less than 4 or equal.
Probably I should put strictly above 2, but it could be in 4. For for small values of n, what I'm saying is true even in 2 dimensions. So the picture is that you have any spin system that flows to the Wilson-Fisher fixed point, and you put an external magnetic field on a few lattice sites. So by the theorem, it cannot be screened. It has to flow to a non-trivial impurity. And an interesting challenge for theory is to predict something about it. There are simulations.
T equals 4, this seems to be a marginal.
Yes, very good. So the answer for D equals 4 is that the bulk fixed point is completely trivial. It's mean field theory. And this is an exactly marginal. It turns out that it's exactly marginal in D equals 4. It's like in the AKLT model in 1+1. It's exactly marginal parameter. Many things depend on it, but there is no renormalization of H. You're completely right. It's a very good observation. So we have recent results from Monte Carlo simulations about this model. I missed actually a few more recent papers. I copied from some references and I missed a few more recent papers. And this is an infrared defect theory with no relevant operators. It's completely stable. Because once you turn on this magnetic field, this operator becomes irrelevant. It's relevant in the UV, and it's irrelevant in the infrared. So what can you do? Just as a theorist, what can you hope to do? You might hope to do what Chenke referred to. You can do epsilon expansion, because near 4 dimensions it's close to being marginal. And you can hope to maybe solve it at large n. It seems like a weird thing to try to solve at large n, because it singles out one component out of n. But surprisingly, after a lot of effort, we actually solved it completely analytically at large n. And so you can hope to do that. I'll just flash the results. In accordance with the G theorem, the infrared fixed point, these are results from the epsilon expansion. In accordance with the G theorem, the quantum dimension is negative. So that's the first example of a negative quantum dimension, I believe, for a conformal impurity. You can already see it in the epsilon expansion. And the defect operator, while as Chenke observed, is relevant in the UV, it becomes irrelevant in the infrared because the defect fixed point is stable to perturbations. Also, interestingly, the coupling H is not small in the epsilon expansion. So it's kind of a tricky epsilon expansion. This coupling is not small. The bulk couplings are small, but this coupling is not small. But since the bulk couplings are small, you can still do the expansion.
It's 4 minus epsilon, right?
Yes, this is 4 minus epsilon. Then at large n, it turns out that there is a two, you can solve it exactly in some, if you assume that H in the infrared scales like square root of n, you can solve this model exactly. It amounts to finding a new classical saddle point. So the literature on the large n vector model that goes back to probably 6 on Zutter or something of that sort is about finding classical saddle points and computing determinants around them. Here there is a new classical saddle point as a result of the magnetic defect. We found it and computed its fluctuations, and that allows to derive exact results. And there is lots of recent work on related exact results in various other large n models like tensor models and SYK and these kind of things. And so these are results from the large n expansion in 2+1 dimensions. You can again see that the quantum dimension is exponentially small, so it's arbitrarily close to 0. And the operator phi1, while its original scaling dimension is half, becomes 1.5. So there is very large renormalization, and that's the large n result. Now, what do simulations show? Simulations by various groups, of which I mentioned 3. I should have put a semicolon here. more or less all agree that the dimension of phi1 is around 1.5, with seemingly a rather weak independence. So the large N results are quite well in the ballpark of simulations at the moment. The simulations could probably be improved.
Sorry, one question, well, maybe these details on the simulation, so they have a cubic lattice, I assume cubic lattice. And you have the drawer circle cubic lattice, right?
You have what?
Drawer-
Oh no, they don't measure log G. There are no
Oh,
simulations for log G. What they measure is the defect dimension phi1,
I see.
and this is measured by computing a Green's function
Yeah, sure.
in the bulk. There are no numerical results whatsoever for log G. It's hard to imagine how would you draw a circle on the
Yeah,
lattice.
exactly.
So you have to understand what to do with the cusps. So I was thinking about it for a few weeks, a couple of months ago. The cusps introduce various logarithmic singularities, you need to subtract them. It's like asking why do people on the lattice don't measure the cusp anomalous dimension. It's tricky. So I don't really know if log G is definitely measurable on the lattice, but you have to understand what to do with the corners. There are no numerical results for it for now. Okay, now I'll quickly mention very briefly. Maybe I wanted to say something about the condo type defect where you put an external spin. Let me skip that. I'll just decide. Somebody wants to know that later. But actually here, the reason I want to tell you about it was that here actually a prediction was recently verified by simulation by Adam Nahum and Weber and Wojta. So this was a nice story, but I want to skip it. I want to tell you something about charged impurities. This is relevant for deconfined critical points where there is a gauge field in the bulk. So when there is a gauge field in the bulk, you can do this gauging procedure. So you can gauge the symmetry of a quantum mechanical model, and you get the charged particle. You just want to know the response to a charged particle in some deconfined critical point. It's obviously going to be perimeter law, but not all the perimeter laws were born equal, because some are trivial defects and some are non-trivial conformal defects. This distinction is not usually made. Okay, so this is what I wanted to say here. People often talk about Wilsonize in relation to diagnostic confinement versus conformal, confined versus deconfined. But that's not the point. When you're in a deconfined critical point, like or a CFT, you should make a finer distinction between Wilsonize that flow to trivial line operators or to non-trivial conformal line operators. So a trivial line operator would strictly have perimeter law for any shape. A non-trivial conformal line operator would scale like the perimeter, but it would depend on ratios, on geometric ratios, not just the perimeter. Okay, so let's do some semi-classics. Let's take a billion, let's just take a gauge field coupled to a four-dimensional massless scalar. So it's like scalar QED in 4 dimensions, 3 plus 1. I'll do 2 plus 1 later. And this is a charged impurity of charge Q. So the usual vacuum of scalar QED is vanishing gauge field, vanishing scalar, obviously. But now, due to the charged impurity, you cannot have a trivial vacuum. So what is the saddle point? It's the high school saddle point. Yeah, it's a Coulomb field. So you put the scalar to 0 and you have a Coulomb field. That sounds like the infrared of this impurity, end of story. It just creates an electric field. So there is a 1-point function for an electric field, end of story. But this turns out to be wrong. If you assume that that answer was correct, you can compute the defect scaling dimension of a bilinear. It sounds like a weird thing to do, but I can explain why that's the right thing to do. So you just assume that this is the correct saddle point, and you can take the scaling dimensions of defect operators just to learn about this conformal impurity, and you encounter the square root formula in some approximation, which is justified. And clearly this becomes imaginary if the charge of the impurity exceeds e squared over 2 pi. So in nature, e squared over 2 pi is like 69. It's 137 divided by 2. So you could say that in scalar QED, if you put an impurity of charge 70, this is not the right saddle point. It just doesn't make sense. There are some imaginary scaling dimensions. So what is the physics? The physics is that if you put an impurity and there is a massless gauge theory around it, it creates such a huge electric field that it leads to the vacuum breaking down, in a sense, via Schwinger's mechanism of pair creation. So therefore, this vacuum is not the right one.
So why do you need a critical charge for that? Shouldn't you for any charge?
It happens only, it's a phase transition. It's an infinite order phase transition at Q equals 70. Before that, the vacuum is fine. You'll see it's he's anxious because he knows that what's coming. It's like it used to be when you enter the conformal window. It just happens suddenly. It's the same here, you'll see outlook. So the reason, the way to describe this sickness is that actually the formula of Wilson was wrong. Just to make a stupid sounding claim. This is not the correct formula for Wilson line. The fact that this operator becomes imaginary, has imaginary scaling dimension. What's more interesting is that it becomes exactly marginal at e squared q over 2 pi equals 1. So just before the transition, it becomes marginal. So in some sense, Wilson was wrong. Okay, like Einstein was wrong. People say it in the news. So somehow Wilson was wrong. It should have added another term to the formula of the Wilson line, which is pi dagger phi. For small nuclei like q equals 3, 4, 5, it doesn't matter because this operator is highly irrelevant and g flows to 0. So Wilson was fine. But if you go to nuclei which are like 70, okay, or 68, 65, this becomes nearly marginal and its renormalization cannot be neglected. So you must add additional terms to the formula of the Wilson line. And we computed the beta function, that's what you get. So just below 70, there are 2 fixed points. So actually there are 2 distinct conformal impurities which are corresponding to an external charge. This was not seen experimentally yet. One is the ordinary hydrogen atom like situation, and one is a new conformal fixed point, which has a relevant operator that can take you to that one. Then these 2 fixed points merge and they disappear into the complex plane. And that's a discontinuous transition, but it's an infinite order transition. Okay, so that's why it doesn't happen just before 69, because then there's still a fixed point. So there is an infrared fixed point. So to understand what happens past this point of the instability, you see that this beta function is positive definite, and it would drag this coupling G to minus infinity, being that beta is positive definite. So we have to understand the physics of adding phi dagger phi on the Wilson line with infinitely negative infinite coefficient. So clearly this would lead to some condensation, mirroring our intuition that there is a Schwinger effect. And this condensation would have a dimensional transmutation. So there will be a huge cloud. There will be a huge cloud that is generated. And this mechanism for dimensional transmutation is called Miransky scaling. It appears in QCD when you exit the conformal window and also in the BKT transition. So there is dimensional transmutation in the physics of these hydrogen-like atoms. They develop a huge cloud of a condensate, which can go all the way to the moon if you put in numbers, just from one atom. This is the picture of the cloud. We simulated it on the computer. We simulated it. So what do you see here? Let me just guide your eye quickly. Initially, the electric field around the impurity is that you know from high school, but that has an instability due to the Schwinger phenomenon. A cloud is created and the electric field is spring to 0. So the infrared limit of the Wilson line is charge 70 and above is trivial line operator, flows to the unit operator. Below 70, it flows to a fixed point, but actually there is more than one fixed point, as I told you. Above 70, it flows to a trivial fixed point. Below 70, there are probably many fixed points. We just found 2, there are probably more. So the electric field is reduced, but it happens on huge scales. This is like in centimeters, I think. It happens on a huge. So this cloud is very long. It happens. It's like dimensional transmutation in a hydrogen-like atom, and the scalar field gets excited. That's the Schwinger phenomenon, and then it also decays to 0. But this decays even slower. This decay is logarithmic, and this decay is very, very slow.
So over these crazy scales, don't you have to worry about the fact that bulk theory was also not conformal?
That's an excellent question. You're correct that there is a little bit of renormalization group running here, but for the theoretical exercise, you can arrange the parameters that the Landau-Fold scale is even further, so you don't care about it. Okay. And the reason that I'm telling you about scalar QED, which is this simple example, is because the same physics happens in the confined critical points in 2+1, which are rigorously conformal. It's completely universal. It also happens in non-abelian gauge theory of chemical force of triangles, which is rigorously conformal. So, and Banks-Zaks theories and all that. So this is always the answer. There is a critical charge above which the line flows to a trivial line. So that's what I'm saying here. The same physics takes place in the like in graphene, in the non-trivial fixed point that presumably exists in graphene, for instance, where NF equals 4. So the same physics exists in 2+1 dimensions in many critical points. So in 4 dimensions, we found that the critical charge is given by the inverse fine structure constant, p squared over 2 pi, up to a factor of 2. In 2+1 dimensions, it's given by the number of species over 2. So this is not exact. We don't have an exact answer for small values of NF. We have an exact answer at large NF.
So NF is the number of 4
Species.
components.
Of Dirac fermion, of Dirac cones.
For each of that has 4 components.
Now you're putting me on. Yeah.
So
Yes, two complex. Yeah. So NF is the number of two, and NF is the number of Dirac fermions in 2+1, and each Dirac fermion is 2-dimensional, where each component is complex. Okay. So actually, the coefficient is not exactly 2. It's 0.512. We found it exactly in the large NF limit, but it's very close to 2. So in 2+1, it's determined by the number of species, more or less, the bound on which Wilson lines exist. Beyond that, they are screened by essentially the same mechanism. Some condensate is created. Thank you so much. Any other questions?
So in QED, if you have fermionic QED,
Yeah, so the 2 pi becomes 4 pi.
2 pi becomes 4 pi.
So this becomes
100.
4 pi. So it becomes 137.
37.
And another difference is that here you see the solution for the cloud. It screens the electric field completely all the way to 0. It's as if there is just no charge. But in the fermionic QED, we were not able to find an analytic solution for the cloud because it's a system of back-reacting fermions. I think it's an open problem still. But we did some approximation via some technique in condensed matter. I forgot the name. But it's the same technique that goes into Friedel oscillations, where you populate the holes in the Fermi surface. I forgot the technical name of that approximation. And what we found is that 138 would not be screened to 0. It would be screened to 137. So the fermions screen only up to the critical charge, not all the way to 0. Now, of course, in nuclear physics, this is all science fiction. There are no nuclei with 137, and the fermions are not massless. But you can do these experiments in graphene. In graphene, e squared over 2 pi is 4. So even a nucleus of charge 6 would already exhibit this screening and this exponentially large tail. And in particular, in graphene.
Sorry, in graphene, the electromagnetic field will still have like a 3+1.
You're completely correct, but it turns out it doesn't matter.
Okay.
It doesn't matter at all. It still remains at e squared over 4 pi. And you just use the fine structure constant. We have a whole section in the paper about the graphene case where the fermions are in 3D and the gauge field is in 4D. It doesn't matter. So in graphene, this phenomenon should be observable. In particular, there should be 2 fixed points for nuclei that are below 5, like a nucleus at 4. You should see these 2 fixed points. So there should be some logarithms in the phase shift when you scatter from nuclei. I don't think this was observed yet. The fact that there is some screening, if you go above 5 in graphene, was already observed by Levitov a few years ago. They put a huge nucleus and they saw that there is a cloud of charge that's forming around it. So this was observed, I believe, but this was not yet.
Levitov did the experiment?
No, Levitov wrote the theory paper that accompanied the experimental paper. The experiment was done by, I believe, people from MIT.
Do you have any intuition why the screening with massless fermions is so different than with massless scalars?
Yeah, I think the point is that when the bosons have an unstable mode, they're all falling to that unstable mode. And they completely screen. But when the fermions have unstable mode, once one falls in, now there is no unstable mode. So it's like you have the Dirac sea and a hole opens up in the Dirac sea. But once you feel it, you're done.
So it's strong field QED, this dueling potential, or which is corrections to the squared.
What is that? I'm not familiar with that.
So it's a modification of the 1/r squared. Which is strong when you have large C.
Oh, large Z, okay.
And so there's one interpret this.
Yeah, maybe it's related.
It is.
I mean, I'm sure that in some way this is all, no,
Yeah, so
I'm just interpreting it in their language of conformal line operators. I'm sure that people that look at strong field QED know some of this stuff. But we looked at that literature very carefully, and we didn't find a cloud solution, for instance, anywhere. And
for your scalar QED, do you assume that theory as a bulk?
yes,
Then you assume CFD, right?
yes. It's not strictly speaking true because of the Landau pole and the running of the quartic interaction.
It means you consider some phase transition to superconductor or something.
No, it's at a fixed point. You know that there is no actually fixed point.
Yeah,
In 3+1 dimensions.
So I was
So look, but the point is that there is a weakly first order transition to a superconductor.
Yes.
Between superconductor and a deconfined gauge field, right?
Yes.
But there is some scale in that transition, and it's exponentially small. It's basically the Landau pole scale. So what we did is just a way to exhibit the main physics without getting into technicalities. I don't have a slide about it, but what we did is that we assumed that scale of the weakly first order transition is even smaller.
I see. So you assume it's like a second order.
Yes, we just assumed it's second order to a great approximation because the scale of the weakly first order transition. So you can see it in this formula. For us, for this to be true, you need to keep E squared Q fixed. But the scale of the first order transition is e to the minus the fine structure constant. So we basically assume that double scaling limit where E squared Q is fixed, but E squared goes to 0. And then theoretically you're in completely fine grounds. But even if you don't like it, it doesn't matter because the same physics happens in actually correct second order transitions, 2+1. And also in n equals 4 superangles, which is a CFD.
Another thing is, what do you think if you consider some vortex which have some topological constraint or circling one?
So yeah, I mentioned this.
Impurity or general, right?
Yeah.
Defect, but what about some consider some vortex which have some topological constraint? Or maybe
So I mentioned that I'm not going to talk about it. I'm going to talk about it offline.
Okay.
I'm thinking about it now to
Oh, yeah.
understand the phase diagram as a
Yeah.
function of H. So I started thinking about it because Meng Cheng from Yale published simulations
Oh, I see.
of this work. They call that disorder defects. He published simulations in the XY model,
Oh, yeah.
and I wasn't had some things that there seem to contradict unitarity. So I wanted to.
We don't want to maybe no trivial. So
Yes. Yeah, it has to be a non-trivial fixed point for any H that's not 0 or 1.
Yeah.
And the question is to find what's the spectrum of defect operators, what's the G function. I believe, there are some simulations recently about it.
Thank you.